The most powerful conventional bomb ever forged costs $14 million and can punch through 60 meters of solid, reinforced concrete. There is just one massive engineering problem. The target it was built to destroy sites 90 meters deep inside a mountain of solid granite. That 30-meter gap isn't just rock. It is the absolute physical limit of modern kinetic warfare. On the surface, it looks like an impossible standoff. But military engineers have engaged in a high-stakes duel between brute kinetic energy and planetary geology.
How did Iran engineer its Fordow nuclear facility to survive a weapon that cannot physically reach it?
To understand how a facility can survive the most destructive forces humans can launch, you have to look past political rhetoric and analyze the raw structural mechanics of Earth versus physics. Early facilities were constructed at shallow depths, such as Natanz buried 40 to 50 meters beneath the ground. While those early complexes provided protection, advances in warhead metallurgy and precision guidance quickly erased that defensive margin, forcing engineers to push deeper into the planet than ever thought possible. That principle eventually led to facilities buried beneath massive mountains, including the heavily protected Fordow complex, located deep underground beneath layers of rock. Imagine placing an industrial facility beneath a 25-story building made entirely of stone. The entire mountain is the building. And that changes everything. When engineers excavate deep underground, they create enormous caverns inside rock, already carrying the weight of the mountain above it. Tunnels and chambers can be reinforced with rock bolts, concrete, steel supports, and engineered arches. Instead of allowing enormous forces to concentrate at a single point, these structures distribute loads through the surrounding geological mass. The mountain itself becomes the first line of defense against attack. Granite is dense and capable of absorbing and redirecting enormous amounts of energy through cracking and deformation. A blast that devastates a surface structure still has to travel through all that rock before it can reach anything inside. But surviving the outside is only half the problem, because underground engineering creates another nightmare: heat. Inside these facilities, sensitive equipment operates continuously in confined spaces. High-speed centrifuges generate heat while demanding stable power, ventilation, and environmental conditions. Above ground, engineers can exchange air with the atmosphere. Deep underground, every connection to the surface becomes a potential weakness. Ventilation shafts can become vulnerable pathways. Access tunnels can transmit pressure waves. Power and cooling must keep functioning under attack. So the engineering problem becomes a balancing act. How do you create a facility connected enough to operate, but isolated enough to survive? That is why underground complexes rely on layered systems, reinforced tunnels, controlled ventilation, protected entrances, redundant infrastructure, and blast-resistant doors. And that brings us to the weapon designed to defeat hardened underground targets. The American GBU-57 massive Ordnance Penetrator is a 6-meter-long weapon weighing around 13,000 kilograms. Its purpose is brutally simple: get through the surface, survive the impact, and deliver enormous destructive energy deep into the target. But there is an important distinction. Penetrating concrete is not the same as penetrating a mountain. A weapon can be effective against one material without having unlimited ability to defeat every geological environment. As the penetrator encounters dense rock, enormous forces act against it. Energy is absorbed through deformation, fracturing, heat, and vibration. And every additional meter becomes harder. That is the fundamental advantage of depth. It does not make a facility indestructible. It makes the attacker pay an increasingly severe physical price to reach it. So what happens when the weapon cannot reliably reach the main chambers? The strategy changes. Instead of trying to destroy the mountain, attackers can target what connects the mountain to the outside world. Entrances, ventilation shafts, access routes, surface infrastructure. Collapse those systems, and the facility can become isolated even if its deepest chambers remain structurally intact. But isolation is not the same as destruction. A blocked entrance can potentially be cleared, a damaged tunnel can potentially be repaired. Engineers do not necessarily need to restore the exact same route. If excavation equipment and resources remain available, alternative access routes can eventually be created, which creates a remarkable paradox. The deeper you build, the harder the facility is to destroy, but the harder it becomes to operate. And that is where the story takes an unexpected turn. Because one of the most famous attacks against Iran's nuclear infrastructure did not need to penetrate the mountain at all. It entered through software. Stuxnet demonstrated that a cyber attack could bypass physical defenses by targeting the industrial control systems operating inside the facility. Instead of breaking through meters of rock, the attack manipulated the machinery itself. The mountain remained standing. The centrifuges themselves were the target. That was a profound engineering lesson. The strongest physical barrier in the world can protect machinery from a bomb, but it cannot automatically protect that machinery from code. And once engineers understand that, the concept of underground defense expands again. The future is not a single bunker. It can be an entire underground ecosystem. Across Iran, underground military infrastructure has been developed to shelter missiles, vehicles, equipment, fuel, and personnel beneath the surface. Some facilities are connected by underground passages and protected entrances, allowing mobile systems to move while concealed from aerial observation. If the enemy can see you, hide. If the enemy can reach you, go deeper. And if the enemy can attack your hardware, protect the software controlling it. This creates an arms race unlike almost any other. On one side, engineers develop heavier penetrators, precise guidance systems, and powerful delivery platforms. Defenders respond with deeper excavation, stronger structures, redundant systems, and underground networks. The battlefield becomes less about destroying one object and more about overcoming layers of protection. Surface, concrete, rock, depth, infrastructure.
And finally, the systems operating inside.
Underground engineering creates a difficult problem. You can build a bigger bomb, but the defender can dig deeper. You can improve penetration. The defender can choose stronger geology. You can destroy an entrance. The defender can build another. You can attack the machinery. The defender can isolate and harden the systems controlling it. Every solution creates another engineering problem. Modern warfare is not simply a contest between the biggest weapon and strongest bunker. It is a contest between engineering disciplines. Weapons engineers try to concentrate more energy into smaller spaces. Civil engineers try to distribute that energy through larger geological structures. Cyber engineers try to bypass physical barriers entirely. And underground architects respond by creating systems that can survive without the outside world. The mountain is no longer just a mountain. It is part of the machine. How powerful does a weapon need to become before it can defeat an underground nuclear installation protected by layers of solid granite? And how deep can engineers go before digging deeper becomes harder than attacking them? Because this race has no obvious finish line. The attacker increases destructive capability further. The defender adds another layer of earth. And somewhere between the weapon and the mountain lies the ultimate limit of modern engineering.
So what do you think? Will future weapons eventually overcome even the deepest underground facilities? Or will engineers simply keep digging until the Earth itself becomes the ultimate bunker? Drop your answer below today. And subscribe for more engineering stories.